Hi everyone, welcome to Integral Calculus. Today we explore lesson 5.2, definite integrals, part 2. 1. The definite integral. Let's say we have a function fx and we want to compute the area under the curve from A to B. Then we can use the Riemann sum. Limit n go to infinity. Summation I equal 1 to n of the area of a sample rectangle. Let's take a look at this sample rectangle here. We have the width is delta x, the length fxi. Okay. Lucky for us, there was another German mathematician, Leibniz, and he invented a new notation to compute the sum as the integral. It looks like sum, right? From, well, a to b fx dx. And you can see here that in a sample rectangle, the length is fx, the width is dx. From the previous example, we see that if the area is below the x-axis, then this would have a negative value. And area above the x-axis, then it would have a positive value. Right? There are many properties. First one, integral a to b fx dx gonna be negative of the integral b to a fx dx. Second one, integral, well, from the same number, it would be 0. Third one, integral a to b of a constant c dx. Remember, integral is the area, the function is a constant function, so the area is just going to be a length times width, right? C times b minus a. D, the integral a to b fx plus or minus gx dx. We can split out the integral because integral is just limit of the Riemann sum. Integral a to b fx dx plus or minus integral a to b gx dx. E, integral a to b c fx. We can move the constant outside. C, integral a to b fx dx. Last one. Integral a to b fx dx can be written as integral a to c fx dx plus integral c to b fx dx, where c is in the interval from a to b. Okay. Let's do a few examples. A. Compute integral 0 to 1 4 plus 3 x squared dx. Okay, and we can sketch out this function, see what it look like. X, y. This is a parabola. When you add 4 to the parabola, you shift up by 4. And when you multiply by 3, it's just getting skinnier because the slope is steeper. Zero to 1. So this one is the area right here. Okay. Area equal integral from 0 to 1. 4 plus 3 x squared dx. Now we're going to be using properties of integration. Split this out into integral 0 to 1, 4 plus 3 go in front of the integral 0 to 1 x squared dx. And then 4 here is 4 dx. Oh, well, if we integrate a constant function, it's just going to be a 4 times 1 minus 0 area under the curve plus 3. And this one, in order to do the computation, we're going to use the limit of the Riemann sum. So limit n go to infinity, summation I equal 1 to n fxi delta x. So we have 4 plus 3, limit n go to infinity. Here, delta x is 1 minus 0 over n, 1 over n. xi is a plus I delta x, so that be 0 plus I 1 over n. Okay. So just have a I 1 over n I. Do the substitution, and we're going to have a summation I equal 1 to n f of 1 over n I times 1 over n. 4 plus 3, limit n go to infinity. Summation I equal 1 to n. Plug it into the function, and then remember the function here is the x squared. Right? fx equal x squared. 1 over n I square times 1 over n. 4 plus 3 times limit n go to infinity. 1 over n squared, 1 over n squared, 1 over n squared times 1 over n is 1 over n to the power 3. Okay. And we have summation I equal 1 to n I square. 4 plus 3 limit n go to infinity. 1 over n to the 3. Well, using a summation formula, we have n plus 1 to n plus 1 over 6. And then similarly, the exponent of n on the top is the same as the bottom. So the limit would just be the quotient of the leading coefficient, 2 over 6. So we have a 4 plus 1 and ta-da, 5. Integral 0 to 1 x to the 3 minus 2x dx equal negative 3 over 4 by integral 0 to 1 4x minus 2x to the 3 dx. We can do this. So that is the 0 to 1, and then we want the form to be the same, so I'm going to factor out the negative 2. So factor negative 2, and this can be written as x to the 3 minus 2x dx. So now using property of integral, I'm going to take the negative 2 outside. 0 to 1 x to the 3 minus 2x dx, and ta-da, we have negative 2 multiplied by negative 3 over 4. That gives us 3 over 2. Okay. Here comes another one. Integral 1 to 0 2x minus x to the 3 dx. Well, first thing is that we can switch the limit, because limit is usually written from a smaller number to a bigger number. When we switch limit, we put a negative in front. 0 to 1. Two x minus x to the 3 dx. We can distribute the negative 1 in. This is the same as 0 to 1 negative 2x minus x to the 3 dx, and 0 to 1 x to the 3 minus 2x dx, which is exactly negative 3 over 4. Pretty cool, huh? Let's take a look at another one. C. Given integral 0 to 2 x squared plus 1 dx equal 14 over 3 by integral 0 to 2 x squared plus 4 dx. Oh man, how do we go to do this one? Well, we only know the integral from 0 to 2 of x squared plus 1 dx. So we can split 4 into 1 plus 3, 0 to 2, x squared plus 1 plus 3 dx. Now use property of integral. Split this into two integrals, 0 to 2, x squared plus 1 dx plus integral 0 to 2, 3 dx. So now we have 14 over 3 plus 3 times 2 minus 0. So 14 over 3 plus 6. And that would give us 6. I'm going to multiply this by 3 over 3. So 18. 18 plus 14 is 32 over 3. Here come another one. Integral 2 to 0 x squared minus 1 dx. We're going to use the same trick. And that is, we can turn the x squared minus 1 into x squared plus 1 minus 2. X squared plus 1 minus 2 dx. And then for the integral, you go from 0 to 2, put a negative in front. Now split the integral. It's going to be a negative integral 0 to 2 x squared plus 1 dx minus integral 0 to 2 negative 2 dx negative 14 over 3 minus, it is the minus 2 multiplied to 2 minus 0. And we have negative 14 over 3 plus 4. So 4, I'm going to multiply by 3 over 3 here, common denominator. And we have negative 2 over 3. Super cool. One more. Let's take a look at D. We have a function that look like this. And this function is the symmetric about origin. Let's say here, it's negative 1. It is 1. Given integral from 0 to 1 fx dx equal a. 1 phi I integral from negative 1 to 1 fx dx. We can split this into integral from negative 1 to 0 fx dx plus integral from 0 to 1 fx dx. We know the integral from 0 to 1 is a. That is the area above the x-axis. Integral from -1 to 0 is the area below the x-axis. And because the graph is symmetric about the origin, it would have the same exact area. However, since it is below the x-axis, it's going to be -8. So together, we're going to get 0. And for a function that's symmetric about the origin, hopefully you still remember from pre-calculus, f native x is native fx, or fx is odd function. Pretty cool, huh? Next one. Well, what happened if we want to do a native 1 to 1 absolute value of fx dx? Same thing here, huh? We're going to cut this into 2 different regions. 2 different integral. -1 to 0 absolute value fx dx plus 0 to 1. Well, for the integral from 0 to 1, the function is above the x-axis, so we don't need the absolute value. Fx dx. We know the area below the x-axis is -a. However, with the absolute value, we're gonna get a, and this is a. So together, 2a. Thank you for watching. I hope you found the content useful. Please like and subscribe to help the channel grow. I'll see you in the next video.